Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology. In our today's session, we are going to discuss about the three-phase AC circuit where the subject is the basic electrical engineering. Now, in our previous session, we have already discussed the generation of three-phase AC signal, how the generation of three-phase AC signal can be possible within a same assembly as that of we learn about the single-phase AC generation. Now, if you talk about the three-phase AC generation, and once the generation is done, then we have to distribute this three-phase AC signal to the load. Before that, we have to start with the design of circuit, how the three-phase AC signal will be generated from a kind of circuits. Those circuits we define as a three-phase AC circuits, right? So let us start with the our content. So far we have learned about the introduction of three-phase AC circuits. Then in our today's session we are going to learn about the three-phase star connection. Then we learn about the three-phase delta circuit, and then power measurement of this three-phase AC circuit. So let us start with the three-phase star AC circuit. So some of the important definitions we need to understand in a three-phase AC circuit, like what about the balanced load? The load has the same or equal impedance, right? Then unbalanced load, we code this is a different and not same as the load. So here the condition is that many impedances in the circuit, that means the load is same, that means the value of impedances are same throughout the circuit, that means it is a balanced load. If the impedances are not same, that means it is an unbalanced load. Likewise, we learn about the balanced phase voltage, nothing but all the phase voltages are equal in magnitude and out of the phase with each other by 120 degree. Balanced load current, that means all phase currents are same in a magnitude and all are in out of phase with 120 degree with each other. So these are the common definitions of balanced load, balanced phase voltages and balanced phase current. Same terminology if you talk about in terms of the introduction, where if we are going to learn about the three-phase AC circuit, so it is categorized into two types. One type is called the star connection, another type we define as a delta connection, right? Where this is nothing but in terms of the shape, where why this is very important, because once you generate the three phase straight away, you cannot deliver that three phase to a common load, where you have to distribute the load in a specific shape, right? So if your generation is in a star connection of three phase AC signal, or it is a delta connection of three phase AC signal, then your distribution at load is also a star and delta. Likewise, you need to understand. So here, this is nothing but we have to always design a kind of balanced distributed electrical circuit where loss and load both are in a star connection or both are in a delta connection. So likewise, if you talk about the more about this star connection, where it is the similar ends, either start or finish of the three windings, are connected to a common point, and that common point we define as a neutral point, right? So here sometimes it is also considered as a three-wire connection or a four-wire connection, right? So here what we are going to take one the each end of the one phase, it is connected with the common terminal, and that terminal we define as a neutral terminal. So once you carry out this particular circuit and draw this particular or design this particular star network, that can be look like this way, where you can see where there are three phases are connected in a star shape, and one of the phase we define as a phase A, another phase we define as a phase B, and third phase we define as a phase C, where one end of all these three phases are connected with the one common point, and that common point we define as a neutral point. You can see here how it can be categorized, where see in terms of the circuit diagram, see both are same, where all are connected in a parallel, but the one of the end is connected to the common point, and that common point we define as a neutral common point, right? So if we more consider about the important definition in terms of the star connection, then one of the voltage is called the phase voltage. Now this phase voltage is nothing but the voltage difference or the measured voltage between one of the line and the neutral point, or and the neutral connection is defined as a phase voltage, or phase difference between, or the phase difference appeared across one of the phase is defined as a phase voltage. Same way, the current which is flowing through one of the phase is defined as a phase current. Same way, the line voltage, which is nothing but the voltage difference between two lines, which define as the line voltage, and the line current is nothing but the current flowing through one of the line is defined as the line current. So here the phase voltage we define as either EPH or VPH. The phase current we define as IPH. The line voltage we define as VL or EL, and the line current we define as IL, right? So this terminology if you talk, and let's start with this star connection, where you can see three windings are connected in a star with three phases. Now one of the phase we define as a red phase, another phase we define as a yellow phase, and third phase we define as a blue phase. As in our previous lecture we have discussed about A1, A2, B1, B2 and C1, C2. These three conductors are moving in anti-clockwise direction between two magnets. So here, same here, A1 and A1 and A2 we have replaced by red phase, B1 and B2 we have replaced by yellow phase, C1 and C2 we have replaced by blue phase, right? So here, if we talk about the generation of three phase star connection, that would look like this way. So here, EPH is defined as the phase voltage, which is nothing but the voltage drop across each phase, or the voltage difference across the phase. Same way, here EL is nothing but the line voltage, where voltage difference between two lines. So here, now I define my phases R, Y, B, and my line like red line, yellow line and blue line, right? So according to that, now we have categorized into the current flowing through each phase we define as a phase current IPH, and the current flowing through each line we define as a line current IL. Right, here you can see here IPH is nothing but the current which is flowing through the phase, which is the red phase, and IL is nothing but current which is flowing through the line. So here same way in terms of the voltages, where the voltage across each phase is defined as a phase voltage EPH, and the voltage across two lines we define as a line voltage EL or VH, where IPH, IL, same way here EPH and EL. Right, now based on this recap about the our individual RLC, RLRC and RLC single phase AC circuit, we have discussed these 3 points. Point number 1 is nothing but the relation between voltage and current. But since this is a three phase, we here just need to find the relation of voltage and current of this star as well as data network. So my one of the point is very important point. This is same as like we have discussed during the single phase AC circuit, where relation between IPH and IL and EPH and VL. Right. So this is my point number 1. Same with the point number 2 is nothing but draw the phasor diagram. Here we are not going to draw the waveforms. So point number 3 is a power calculation. So here the overall power calculation of three phase AC signal is nothing but total power is equal to 3 times of the power per phase, right? So here my next theory we need to discuss about the total these 3 points. So let's start with point number 1, where you can see first my job is to find the relationship of phase voltage and line voltage. So if we talk about here, you can see this particular now star network. This is a proper star network, where there are three lines R, Y, B. One of the common point is common terminal is defined as a neutral terminal. So the phase voltages you define here from this particular network, where R, Y, B all are connected as 120 degree apart with each other. So with this respect, if you are finding the phase voltages, line voltages, phase current and line currents, by that way if we discuss further within a same circuit, so you can see here from this particular network here, the phase voltages are nothing but ERN, EYN, EBN and EPH. So I consider here ERN is nothing but the phase difference or the voltage between red phase and neutral common terminal. So that is represented as ERN. Same way from the yellow phase two common terminal, neutral terminal. So here it is defined as a EYN, same way for EBN, and in general it is referred as a EPH. Same way here, if you consider about the phase currents, is nothing but IR, IY, IB, and IPH, right? Same way here, if you talk about the line voltages, is line voltage is nothing but the voltage between two lines. So here I have total three lines: red line, yellow line, and blue line. So the line voltages are nothing but VRY, VYB, and VBR is nothing but in general is considered as a VL. Same way here the line currents are defined as IL1, IL2, IL3, and IL. Now what is IL1? IL1 is nothing but the line 1 that we define as a red line. Same way line 2 is nothing but the yellow line, and line 3 is nothing but the blue line. So here if you talk all this star connection wherein is balanced, that means whatever generation of EMF here, that generation is nothing but the same in magnitude, but 120 degree apart with each other, right? So if all the magnitude of generation of three phase are same, like red phase, yellow phase, and blue phase, all are identical phases where all will generate a same magnitude of AC signal, but all are in a 120 degree apart with each other. In that case, I can consider my phase voltages like ERN is equal to EYN is equal to EBN, and that is equal to EPH in general way. Same if I consider about the phase current, that current is nothing but IR is equal to IY is equal to IB is equal to IPH. Same way line voltages, if I talk about, then here the line voltage is nothing but VRY is equal to VYB is equal to VBR is equal to VL, and the line currents is nothing but IL1 is equal to IL2 is equal to IL3 is equal to IL, if the complete star three phase network is balanced. Right now using this phenomena, if we find the relation of voltage and currents like the phase voltages and phase voltages versus line voltages, and the phase current versus line current, if you talk, this is the same circuit if you define, and in this particular circuit if we find the relation of uh, phase current versus line current, right? So here from this particular network you can see here the in a red phase, that is a flow of current IR, which is called a phase current, and in line 1 see the current IL1. So here I can say the IR is equal to IL1, same way here IY is equal to IL2, same way here IB is equal to IL3. So all the phase currents and all the line currents are same as per the above circuit. So I can say here IPH is equal to IL. Now this is one of the relation of the phase current versus line current for a three phase star network, right? So here the phase current value is same as the line current value in a star connection, right? So from this you can be able to write now here IR is equal to IY is equal to IB is equal to IL, and that is equal to IPH, right? So here the current for both the cases is same. Now if we talk about the phase voltage and line voltage, so from this particular circuit you can if you deduce the you can find this from this equation, like if we want to find the VRY. So here from this particular circuit you can say that VRY is equal to ERN plus EYN, right? Now this is a summation, but in real case this is not a summation. Why? Because the current flowing through red phase and the current flowing through yellow phase both are in opposite directions, right? Since both currents are flowing and since the both currents are in opposite direction, my actual equation of VRY is nothing but E Rn minus EYN, right? So this is called my vector equation. Same way if I'm looking for VYB, and that is equal to EYN minus EBN. If I'm looking for VBR, that is nothing but EBN minus ERN, right? So by that way you can find. Now since this is a vector quantity, so this is not a straight away a summation or subtraction, right? But we have to use the magnitude of this. So here we have to find the phasor diagram of this. So I already told you where you stuck In that condition, only phasor diagram is the master key to solve this particular confusion. So you can see this is the phasor diagram where if you look for VRY is nothing but ERN minus EYN, right? So this one of the vector you can consider as ERN, the above vector ERN, right? Now VYN is here, so Vyn is here, and the opposite direction it becomes the minus Vyn, right? So here you will find total two vector. So from this two vector using the parallelogram method, you can find the resultant vector, and that resultant vector we define as Vry. So you can see the above part is a Vry, where my job is to find the resultant magnitude of this Vry, and that we can find using the parallelogram method. Same way for two more vectors to find, like VYB and VBR, you can find this particular phasor diagram, and from that you can be able to find all together or all line voltage terminology. So once I'm going to solve this line voltage terminology, you can find using the trigonometry or mathematical equation where all this is 120 degree apart with each other. So from this you can be able to find from the phasor diagram, like one of the vector is nothing but available at the angle 30, right? From the total two vector. So from this you will able to find the total equation. Then I can find my total equation. Vry is equal to under root of ERN square plus EYN square plus. Now instead of this I am going to write the 2 into ERN into EYN cos 60, and once you are going to solve this, you can find from the trigonometry the last equation would be Vry is equal to root 3 times of EPH. I can conclude that the line voltage is nothing but the root 3 times of the phase voltage, right? So in that case you will get the same answer like here VBY is equal to root 3 times of EPH. Same way VBR is equal to root 3 times of EPH, of line current versus phase current, line voltage versus phase voltage, where you can see here thus for the star connected system, line voltage is nothing but root 3 times of phase voltage, and line current is nothing but same as line current is same as the phase current, right? Now this two important equation we are going to use to find the power calculation, right? So we have already discussed the phasor diagram. So my point number one is that the find the relation of VL versus EPH and IL versus IPH. That part is done. Point number two is draw the phasor diagram. So this is what it's a phasor diagram. Point number three is we can consider as a power calculation. So let's calculate the power. So total power is nothing but the 3 times of power per phase. So if we simplify this particular equation where you can find VPH into IPH into cos phi. Now this is nothing but the power per phase, right? Now in this case you already found VL is equal to root 3 times of EPH. So here instead of EPH you can write VL by root 3, right? Same way IPH is nothing but IL for a star connection. So for real power, if you want to find the total power of the 3 phase is nothing but the 3 times of power per phase, where you can find 3 EPH into IPH cos phi, and that is total power P is equal to 3 into VL by root 3 into IL into cos phi. Right. Why? Because EPH is equal to VL by root 3 and IPH is equal to IL. So from this you can be able to find the total power of this star connection is nothing but root 3 times of VL IL cos phi. Right. This is about the generation of 3-phase star connection. Thank you very much, dear students. If you find any difficulty, please write in a comment box. Thank you very much.